Hi again. Today we're going to wrap up Chapter 6 and look at the powers of complex numbers. So this is actually really where we're going to use that trigonometric form. So if we had the number z raised to the fifth power and we're using standard form, well, we'd have to do a lot of FOILing, a lot of distribution. So let's look at the pattern of the powers in trigonometric form to see if we could figure out a shortcut. So remember, we have the number z in trigonometric form, r times cosine of theta plus I times sine of theta. And if we're going to square it, well, we have to FOIL and distribute that, but you're going to start to see that we have some Pythagorean identities in there. And this will be simplified into r squared times cosine of 2 times theta plus I times sine of 2 times theta. You'll start to see the 3 here, so we have r cubed, and then you see that angle again being multiplied by 3. And for z to the fourth, well, the r is going to be raised to the fourth, but the angle will be multiplied by 4. So it's very similar to exponential properties. When it's raised to a power, we're multiplying the exponents. So when we're raising this to a power, we're going to be multiplying the angle. Very interesting. So the first person to really figure this out and publish it was de Moivre. So de Moivre's theorem is exactly that. We're using numbers in trigonometric form to find the higher powers. So z to the n, well, that's going to be r to the n times cosine of n times theta plus I times sine of n times theta. So we're going to simplify this number in standard form raised to the 12th using de Moivre's theorem. So the first thing we need to do is write this in trigonometric form. So we need to find the modulus. So that's just going to be the square root of 1 plus 3, which is just 4, so that's 2. We know that this angle is going to be in the second quadrant, right? So finding that angle, we just have to use our tangent or just figure out the angle, but it's going to be root 3 over negative 1, and we know that's going to be 135 or 2 pi over 3. So this number in trigonometric form would be 2 times the cosine of 2 pi over 3 plus I times sine of 2 pi over 3. Now we want to raise this number to the 12th power. So z to the 12th power, well, that's just, we have to raise 2 to the 12th power. And we're going to multiply these angles by 12. Let's see if I could just put that in parentheses there. So we'll have cosine 12 times 2 pi over 3 plus I times sine of 12 times 2 pi over 3. So when we simplify this, we're going to get, this is 4,096, and this is cosine, well, that's going to be 8 pi. You could write 2 pi or 0, right? So knowing that, we know the cosine is equal to 1 when the angle is 0. So this will be 1, and then the sine is 0, so that's just going to cancel out. So this is going to simplify into 4,096. Very interesting and very fun. So very helpful to use de Moivre's theorem when finding higher powers of complex numbers. Now let's consider the roots. So if we look at the nth root of a complex number, we actually can figure out the formula as well. So remember, if we have something like x to the 6 equals 1, well, that means that we know by the fundamental theorem of algebra that this will have 6 roots, but they may not all be real, right? They can be complex, but we will have 6 distinct roots. So when we have a complex number, we actually can also find more easily those roots. So what I'd like to do is kind of look at this proof here. So if we know that the number z, that's going to be our number, right? Our complex number. So we know that's r times cosine of theta plus I times sine of theta. And we want to say that one of its roots, u, we'll just use some other letters. So s, and I'll put cosine of beta plus I sine of beta. So if we say that u to the n equals z, then we can say, well, s to the n, using de Moivre's theorem, cosine of n times beta plus I times sine of n times beta is going to equal r times cosine of theta plus I times sine of theta. Well, if we knew that those are equal, we know that these two, s of n and r, would equal each other, and they can cancel each other out. And then so we can actually use some matching here. So we know n times theta, or n times beta equals theta, and then plus 2 pi k, because remember it's going to repeat every 2 pi because the period of cosine and sine are both 2 pi. So that's going to keep repeating. So if I want to isolate beta, well, beta is going to be theta plus 2 pi k over n, right? So divide both sides by n. And that's actually going to help us figure out those roots. So the formula to find those roots, let's scroll back over here. So we know that this number, if it's a root, we have to find that nth root of r. But looking at the angles, you can see that this angle here is going to be equal to theta plus 2 pi k over n. And n is the number of roots that we're trying to find. All right, so now let's find all 6 roots of 1. So if we want to find 6 roots, our n will equal 6. And in complex form, well, we first need to find the modulus, and that's just going to be 1. And we know that that radius equals 1, or x equals 1, when the angle is 0. So in trigonometric form, this would be 1 times cosine of 0 plus I times sine of 0. So if we want to find the 6 roots, for every root, we're going to take the 6th root of 1, and then we're going to multiply this by the cosine of 0 plus 2 pi k over 6, because we have 6 roots, plus I times the sine of 0 plus 2 pi k over 6. All right, let's start with the first root. So z sub 1. So we're just going to have 1 in that modulus. So of cosine of 2 pi over 6, so that's pi over 3, plus I times the sine of pi over 3. And we know the cosine of pi over 3 is 1/2, and the sine is root 3 over 2 times I. There you go, put it at the end. And then z sub 2, well, that's going to be cosine of 2 pi over times 4, so 4 pi over 6, that'll be 2 pi over 3 plus I times sine of 2 pi over 3. So we know that 2 pi over 3, the cosine is now going to be negative, but the sine is still positive. All right, let's look at the third root. So again, we're multiplying that k by 3, so that's going to be 6 pi over 6, so that's going to be cosine of pi plus I times sine of pi. And we know the cosine at pi is -1, while the sine is 0, so that just equals -1. And then for 4, we'll have 8 pi over 6, so 4 pi over 3. You can see that this is adding pi over 3 each time. All right, and so looking at the 4 pi over 3, we know that that cosine is going to be negative. Well, both of them will be negative. So of -1/2 minus root 3 over 2i. All right, adding another pi over 3, start to see this pattern. We have 5 pi over 3 plus I times the sine of 5 pi over 3. Cosine is now positive, sine is negative. And then let's do the 6th root. So this will be cosine, adding that, so we'll get back to 2 pi, which is really 0, right? So I times sine of 2 pi, and we're going to get back to 1. So you can see that we're going to have 6 roots, right? because we're finding the sixth root, but obviously many of them are imaginary. But you know that the two roots that are real are -1 and 1. Now for our final example. So for this one, we're going to find the 3 cube roots. So our n is 3 for this complex number, -2 plus 2y. So we know that that would take us into the second quadrant. And if this is 2, -2, this must be 135. So our angle is 135. Or you could say 3 pi over 4. And then looking at the radius, well, that's just going to be, or the modulus, it's going to be square root of 8, right? 4 plus 4, or 2 root 2. I'm going to leave it in square root of 8 because we actually need to take the cube root of that, which gets kind of messy. So for any of these roots, the k roots, we're going to take the cube root of the square root of 8, and we're going to have the cosine of 135 plus 360 times k over 3 plus I times sine of 135 plus 360 k over 3. And now again, you could put that in radians. Okay, what I'd like to do first is simplify this guy. So that's going to be 8 to the 1/2 to the 1/3. So we know that that's 8 to the 1/6. And we can simplify 8, right? That's 2 cubed. So 2 cubed would be 2 to the 3/6, or 2 to the 1/2, which is square root of 2. All right, so we're going to simplify that to square root of 2. So looking at the first root, it's going to be square root of 2. Square root of 2 is going to be the modulus for all of these. And so when I plug in 1, we get cosine 165 plus I sine of 165. And so if I simplify that, well, we can't calculate that because that's not a special triangle. I mean, we don't know it right off the, right off the top of our minds. We'd have to use a formula. So I'm going to show you how to use the formula, but you can also find the decimal at this point. It gets a little messy. So I'm just going to say for this kind of problem, we're going to use the decimal. All right, so simplifying that, because it's not a 30, 60, 90, well, we're going to get square root of 2 times cosine of 165, so that's going to be -1.366 plus 0.366i. Okay, so that's the first root. If we're going to use the sum and difference formulas, we can. I'm not going to ask you to do this, but just as a refresher, we can rewrite this as cosine of 165, so that's going to be 135 plus 30 plus I times the sine of 135 plus 30. And then we can use those sum formulas from chapter 5. So we have square root of 2, so that's going to be cosine of 135 times the cosine of 30. So it's getting a little sloppy. Use the formula, so it's minus sine of 135 cosine sine of 30. I think I'm going to run out of room here, so I'm going to just write this here. So I times the sine of 135 times the cosine of 30. Just using parentheses to try to separate that. And then cosine of 135 times the sine of 30. So I'm going to write this out. So we have square root of 2. Cosine of 135, that's just going to be -√2 over 2. And then cosine of 30 is √3 over 2. Minus sine of 135, that's going to be positive √2 over 2 times the sine of 30, so that's 1/2 times there. And then we're going to have the I times the sine, so this is going to be √2 over 2. It's positive. Cosine again is √3 over 2. Cosine of 135 is negative. Put negative here. √2 over 2. And then the sine of 30 is 1/2. All right, so looking at this, you can see where we're going to start using decimals on this particular problem, but we have negative root 6 minus root 2 over 4 plus I times root 6 minus root 2 over 4. All right, so for these sorts of problems, we're not going to use the sum difference formulas that we learned before just to save time because we're not really testing on that for this section, but you definitely use those power rules to find those roots. Okay, so that's the first one. And so let's look at the second one. So z sub 2 is going to be the square root of 2 times cosine. I'm going to zoom in here so I have room. 135 plus 360 times 2 over 3. And then that's going to be the same thing here. I sine 135 plus 360 times 2 over 3. So this is going to simplify to equal cosine of 285 plus I times the sine of 285. And again, that's not an easy decimal, an easy value to find with 3690 or 4545 with special triangles. So we're going to simplify this with decimals, so that's 0.366 plus, or minus, sorry, 1.366 I. All right, now the third root is going to actually just take us back, and we could have started with that one when we first started. So that's going to be square root of 2 times cosine of 130 over, or 135 over 3. So square root of 2 cosine of 135, that's going to be 45 over 3. So I sine 135 over 3. So we're going to come back to 45. So this is root 2 cosine of 45. I times sine of 45. Special triangles, we could do that one. So root 2 over 2 plus I times root 2 over 2. So that's just going to be 1 plus I. So there we have our 3 roots for the complex number negative 2 plus 2I. All right, well, that's it for this lesson. I hope it was helpful, and I'll see you all in class.